It's time for a Europa Fest. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. We're now just 2 months away from the highly anticipated launch of NASA's Europa Clipper mission. This week, we're going to take a look back at over 20 years of Planetary Radio episodes about Europa, as we cheer on the scientists who have worked so hard to bring us to this moment. That means you'll hear from me, but also Planetary Radio's creator and previous host, Matt Kaplan. Then Bruce Betts, our chief scientist, will join me for What's Up as I gear up for my trip to next week's NASA Innovative Advanced Concept Symposium. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Jupiter's icy moon Europa has captivated humanity for hundreds of years. Interest in Europa dates back to 1610, when Italian astronomer Galileo Galilei aimed his homemade telescope at Jupiter and discovered the now famous Galilean moons, Io, Europa, Ganymede, and Callisto. Centuries later, the Voyager spacecrafts imaged Europa during their flybys of the Jovian system in 1979. Both Voyager 1 and Voyager 2 captured detailed images of that moon, revealing its smooth, icy surface. Those images were the ones that sparked the interest in Europa as a potentially habitable world with a subsurface ocean. Since then, we've had several missions to the Jovian system, each of them providing even more insights into Jupiter and its moons. In 1989, NASA launched the Galileo spacecraft. Data from that mission to Jupiter indicated even more strongly that beneath Europa's icy surface might lie a subsurface ocean containing more water than we have in all of Earth's oceans combined. Then, in 2011, NASA's Juno mission blasted off to explore Jupiter in more detail. Along the way, it grabbed a bunch of images of Europa and other moons. Juno's still out there in the Jovian system exploring to this day. And of course, in 2023, the European Space Agency's Jupiter Icy Moons Explorer, or JUICE mission, took off for Jupiter. That mission is still cruising its way through space on its way to Jupiter now. While all of these missions have been groundbreaking in their own right, a dedicated Europa mission has been the dream of planetary scientists for decades. And now, finally, after years of advocacy from scientists and space enthusiasts alike, the Europa Clipper mission will soon take off from Florida in October, on a journey to investigate one of the most intriguing moons humanity has ever encountered. Europa Clipper is managed by Caltech near our headquarters in Pasadena, California. NASA's Jet Propulsion Laboratory leads the development of Europa Clipper in partnership with the Johns Hopkins Applied Physics Lab. APL designed the main spacecraft with the help of JPL, Goddard Space Flight Center, Marshall Space Flight Center, and the Langley Research Center. It's been a big team effort. The Europa Clipper engineers and technicians deployed and tested the spacecraft's giant solar arrays in late August 2024. The moment is almost here. To mark this momentous occasion, today we're going to take a look back at over 20 years of Planetary Radio interviews about Europa. From the days when a dedicated Europa mission was just a twinkle in the eye of a planetary scientist, to the moment that Bob Pappalardo, project scientist for Europa Clipper, visited Planetary Society headquarters to show off the beautiful message that humanity would be sending on that mission, inscribed on the vault plate that will protect the mission's instruments as it orbits Jupiter. We begin over 2 decades ago in 2003, when Elizabeth or Zibi Turtle joined a fledgling Planetary Radio to talk about the ices of Europa. At the time, she was a senior research associate in the Department of Planetary Sciences at the Lunar and Planetary Lab at the University of Arizona. She went on to become a planetary scientist at Johns Hopkins Applied Physics Lab and became the principal investigator of the upcoming Dragonfly mission to Saturn's moon Titan. At the time of this interview, we weren't entirely sure yet that Europa had a subsurface ocean.
Yes, there may in fact be liquid water under the ice shell on Europa. There's several lines of evidence that suggest that.
I guess we've certainly determined, because we've had good observations, that Europa seems to be encased in this layer of ice. But for one thing, how do we have any idea how thick that ice is, and how do we have any idea that it is water and that there's liquid water underneath it?
We know from spectroscopic observations that it's water ice, and we know how much water and ice there is, liquid and solid there is, from gravity measurements, actually, that the Galileo spacecraft made as it flew by Europa. So we know there's an outer layer of solid and liquid water that's somewhere between 80 and 170 kilometers thick. Unfortunately, the gravity can't distinguish between the phases of the water, whether that's liquid or solid. But there are other lines of evidence, such as the surface geology and the use of the surface, that have suggested that there's still liquid water underlying the ice. When we simulated the later stages of the impact cratering process, what we found is that as the impact crater opens up, the ice isn't breached. However, often as the impact crater collapses back, the water does breach the surface if the ice is thin enough. And our results indicate that if the thickness of the ice is comparable to the diameter of the initial crater cavity that's opened up, then the ice can be breached by water as the crater collapses late in the impact cratering process. Now, when I say late in the impact cratering process, I should specify that that's only a few minutes. Impact cratering is a very rapid process, so late is on the order of a couple of minutes. And what this means is that in order for craters of the morphology we observe on Europa to form, the ice really needs to be at least 10 to 15 kilometers thick.
Oh, I see. Well, that strikes me as a finding in and of itself that is going to be useful in research elsewhere in the solar system, perhaps beyond someday. But that conclusion that the ice may be quite a bit thicker than some people were hoping must come as a disappointment to some folks who would love to drill down through that ice, get into that ocean, and find out what might be in there.
Yes, it certainly makes it harder to get to the liquid water that we believe is beneath the ice. However, what we looked at on Europa is only a few impact craters. There only are a few impact craters, and those can only constrain the ice thickness at the locations and the times at which they formed. There may well be other places on Europa where the ice is thinner, so it doesn't rule out the possibility that one could get through to a water layer in some locations on Europa.
I see.
Can't rule that out.
So we should not
That's where the impact craters form.
We should not assume that layer of ice is the same thickness all the way around.
It may not be.
Yeah.
Shortly after Zibi joined us on the show, NASA planetary scientist Chris McKay came on. Chris is a senior scientist for NASA Ames Research Center. He speculated about whether Europa, among other worlds in our solar system, could potentially harbor life.
Mars didn't have life, or if the life there was just the same as us, the next place to find an alien life form, a second Genesis, something different, would be, I think, Europa. There, in the ocean that we think exists underneath the icy surface, there may be life there, and the chances of that life sharing a common origin with Earth/Mars maybe is much less. And so if there was a second Genesis, and we don't find it on Mars, maybe we'll find it on Europa.
And so much harder to reach for tourists.
Much harder to reach. It's a long way out there. There's dangerous radiation fields from Jupiter. It's a much harder search on Europa. Then when you reach there, you might find stuff on the surface, or you might have to drill down. It's just a much more daunting task and much harder to imagine a direct role of humans in the search for life on Europa than on Mars.
Now we go forward a few years to 2006. Bob Pappalardo, project scientist for Europa Clipper, had only just begun his time working at NASA's Jet Propulsion Laboratory as a principal scientist. He hoped very much that someday a dedicated mission to Europa would become a reality, but I don't know if he had any clue at the time that he would still be working on it almost 20 years later.
Europa is an incredible place for so many reasons, but the chief one is astrobiology, a critical question in understanding our place in the universe is whether life is common or rare, as the Planetary Society is well aware. Europa, we're pretty sure, say 90% sure or so, that there's an ocean beneath the surface of Europa, the icy surface. There's a chance that Europa has the chemical energy necessary for life. And so Europa is one of the key targets in understanding whether there might be other life in our solar system today, Mars, of course, being the other one. Now we have a large program that's sending spacecraft to Mars every couple of years, but as of the moment, we don't have a follow-up mission to Europa. We're working on that. But the other thing besides the astrobiology, we can talk more about that, is the geophysics. We don't get Europa yet. It's about the most complicated planetary situation that you could think of. It's ice, which has very complicated rheology, the way it flows and behaves. It's tidal interactions with Jupiter. It has resonances with its neighboring moons, Io and Ganymede. It's a complex system to understand. That complexity, that geophysical complexity, is what also makes it astrobiologically interesting, because there is tidal heating, which maintains liquid water below, and activity, which may pump chemical energy into the water and potentially allow for life there.
Well, we were all extremely curious about that big ocean. The surface itself is so fascinating. It's so rich in features that I guess are still puzzling folks like you.
Exactly. Again, we don't get it, and that's what keeps it interesting. Maybe I shouldn't say my favorite moon, if you ask me, is probably Ganymede, okay, Europa's neighbor. We get Ganymede somewhat. We can look at Earth and look at Ganymede and go, okay, I kind of recognize how these types of features might form by extension of the icy crust over more mobile and flowing ice beneath. But we look at Europa and we say, what the heck is that, right? It keeps us investigating. Europa is covered by these double ridges like a plate of spaghetti. They're overlapping one another. But you look at any individual one, and it's not just one ridge, but it's a pair of ridges traveling together across the surface. So what's made this sequence of ridges cross-cutting one another, and especially traveling across the surface in pairs like this? Well, one idea is that the surface has been pushed upward somehow, like a tree root growing beneath an asphalt sidewalk and warping it upward into a double ridge. But then, there aren't trees growing there, so what's underneath pushing up on the surface? And there are various models that involve the combination of water or warm ice to push up the surface, and perhaps even to squeeze out on the surface. And then the other main type of feature on the surface is this mottled terrain, these freckles and spots. Some of the larger ones show evidence that ice plates have been mobile and moved around the surface and translated and rotated. And then there are competing models for that. Again, we don't really understand what's going on. One model says the surface has literally melted from below, that there's enough heat that some of these features are the result of melting, complete melting of the ice crust. Another model, and the one I tend to favor, is that the ice shell is thick enough that it actually convects, overturns like a lava lamp, where warm ice below is tidally heated, comes up toward the surface, colder ice sinks down. You usually don't think of solids flowing, but lava lamp is a nice analogy, or the inside of our planet, right? The Earth is convection.
Sure, yeah.
With warm pockets of rock moving up and colder ones sinking down. So those are some of the models, but again, at meetings and through the scientific literature, there are debates going on. How did these things form? What does this mean for the interior? What does it mean for the plausibility of life, or for that matter, for where we might find life if we were to send a lander to Europa?
I'm assuming that one of the reasons you're happy to be at JPL now is because it may be a really good place for you to try and push this mission to Europa that you and so many people would like to see.
Well, JPL has been taking the lead in looking at the feasibility of such missions and scenarios for mission to Europa. Now, the first mission that we've been talking about, dedicated Europa mission, would be an orbiter. There's the possibility of having a small lander attached, but the key scientific questions we want to get at, the first step, is to do an orbiter. Sort of do for Europa what Mars Global Surveyor did for Mars. We don't have a good idea of the topography of Europa. To confirm whether there's an ocean and really characterize the ice shell and the presumed ocean beneath, we need gravity and altimetry, measuring the distance to the surface, and through measuring the gravity field, understand how Europa is warping tidally as it moves in its eccentric orbit around Jupiter. By measuring the topography and altimetry as Europa orbits, we can characterize that ice shell and the ocean. So you really have to be in orbit around Europa, which is not an easy thing to do, right? You're in the huge gravity well of Jupiter. So it takes a lot of propellant, that takes a lot of mass, and so it's a difficult mission.
Torrance Johnson was the project scientist for the Galileo mission to Jupiter, but he also worked on the Voyager mission team. While the Voyagers gave us a beautiful glimpse of Europa, Galileo gave us our first close-ups. In 2006, Torrance joined us to discuss the state of our technology and whether or not a Europa mission was going to be viable in the upcoming years.
The most recent major survey of the entire planetary science community recommended a Europa orbiter as the highest priority new flagship mission, and they established a number of goals for it, which are fairly obvious. If you've been interested in Europa, you want to find out whether that ocean is really there. You want to find out how deep beneath the ice it is. You want to characterize what's going on. You want to see whether the water has been coming up to the surface recently. You want to take the type of data that would prepare you for the next stage of exploration, just like we're doing on Mars now. Okay, bottom line is with enough mass for shielding, the Europa mission can be done now with current technology that will last long enough to really do an exciting mission at Jupiter and at Europa.
Torrance Johnson had been speaking at NASA Ames Research Center that day. Shortly after, Chris McKay discussed what Europa could mean for comparative astrobiology. At the time, Chris was a researcher at Ames and a member of the Astrobiology Institute.
Why is life on other worlds interesting? What are we hoping to find on Europa? What we're hoping to find on Europa is the possibility that there's a separate type of life there, a second genesis of life. That's what astrobiology would really like to find. Life not as we know it, life different from the life we have on Earth. And why is that interesting? Well, first, from a practical point of view, it would allow us to do comparative biochemistry. Everything we know about biology, everything we know about biochemistry is based on studying the one example we have here on Earth. We could study it in incredible detail and not learn what we would learn by having another example to compare it to. So that would be important scientific information. Also, it would tell us that if in our own solar system life started twice, once on Earth and once on Europa, then life is common in the universe. That's really an interesting thing to know. And I put my little editorial comment there. Yay. That'd be great to know that life is common in the universe. We all think that it's true. Some of us seem to have personal, private evidence that it's true. But scientifically, we don't have any data to support the notion that life is common in the universe. We'd like to know that. On Earth, life is made of carbon and lives in water. Does that mean all life everywhere in the universe has to be based on carbon and live in liquid water? Well, maybe, maybe not. But it knows at least that we know that that's at least a good place to start. And here in our solar system, we've got two worlds with water. That's the logical place to look for life first. That's where we're going. Europa is the target. So I want to ask the question, given liquid water, is it plausible that there was an origin of life on Europa, a separate origin, and is there plausible ecology? Is there something for the folks to be eating there on Europa? The current theory that's the most popular in the scientific community, which is that life started as a result of chemical reactions involving hot water and hydrogen and sulfur, just the sort of thing that's coming out of the vents that John Delaney's studying. That's the most popular theory now for the origin of life on Earth, and that one works well for Europa. So maybe life could have started on Europa. We're on much better ground when we talk about, is there food to eat on Europa? On Europa, below the ice in the ocean, there won't be any light, there won't be any oxygen, and there won't be any free food coming from plants at the surface. Do we have any ecosystems on Earth that work without light and without oxygen? Well, we know of two that work on chemical energy. This reaction is the basis of their biology, is hydrogen plus oxygen going to methane and CO2, and these are just the papers that report that. So we have examples on Earth of ecosystems that are profoundly independent of light and oxygen and don't rely on someone else providing them with food. So could such an ecosystem work on Europa? Yeah, it could. You could imagine that there's water and CO2 in the ocean. The organisms consume that to form methane, just like the ones in the subsurface on Earth, and then thermal circulation, like what John's reporting on the plate spreading centers on Earth, could process that ocean water, and at temperatures as low as 500 degrees, the hydrogen and the CO2 be recreated, completing the cycle. This could be a plausible ecosystem for life in the ocean on Europa. We can point to ecosystems on Earth and say, we have ecosystems, not just individual bugs, but whole ecosystems that work the same way. So if Europa has an ocean, we're pretty sure it does, if that ocean has life, it's going to be hard to get to that ocean. As Bob indicated, the ice may be 20 kilometers thick.
That's a lot of ice to dig through. But Bob also indicated these features, that surface features, that may contain material upwelling through the ice cover. And if so, they may contain biological material that's coming from the ocean. Or as one wag put it, frozen fish on the surface, right? Now, we don't expect fish on the ocean of Europa, but frozen microbial European fish, if you want to think that way.
In the meantime, while the planetary science community was advocating for a Europa mission, scientists on Earth were already working to learn more about what our oceans could teach us about the worlds beyond. Oceanographer John Delaney came onto our show to speak about the challenges of modeling Europa's oceans.
We still have so much more to learn about how the ocean works on this planet. Are we anywhere near the point where we could model it in a place like Europa?
I suspect that it would be possible to develop a suite of models that would not be in any way testable for a number of years, but they may guide the kind of exploration programs we might put together. And I think it would probably be a very valuable effort to have a group of very bright modelers and observationalists and geochemists and at least microbiologists thinking carefully about what the circulation patterns of the European Ocean might be, because therein lies a big piece of whatever the tail will be when we get through the ice. There are first principles, that is, if the ocean is heated from below and it's cooled from the top, then it's going to turn over. If it turns over rapidly enough, then it's not going to be very stratified. In other words, it won't have strong layering of different densities. But that's an open question, and that's a very controversial issue about the dynamics of what the European Ocean might be. There may be other factors that are involved in the patterns of circulation. It's possible that the Coriolis effect enters into the global circulation of the European Ocean, and it's possible that it actually enters into rising plumes that may be coming off of erupting underwater volcanoes. There are an entire host of possible model components that I think could be put together by the right folks, of which I am not one. And the hope is 10 to 20 years from now, we will be able to export much of what we have learned in this robotic, remote sensing, in situ scientific approach that we will be taking into how our own ocean works. And I hope some of that will flow over into a Europa program, which I am desperately hoping will happen before I die.
Flash forward 7 years. Alyssa Rodin, a NASA postdoctoral program fellow for NASA's Goddard Space Flight Center at the time, was studying Jupiter's moon Europa from a distance. She and her colleagues were working on projects to help everyday people help us study Europa. Matt Kaplan asked her why Europa should be our target, rather than going to other tantalizing moons, like Saturn's moon Enceladus.
Why Europa first? Or why Europa next? That's really the question. And I think Enceladus is a large part of the answer to that question. So we went off to the Saturnian system with the Cassini mission, which has just been stellar. And we found this tiny little body. I mean, if you drew it on a map of Earth, it would fit over the British Isle. Okay, I mean, it's a tiny little moon. It's active. It has these jets of water and ice erupting from the South Pole. And all of the models, the theoretical models, said this would never happen, could never happen. Such a small body would have cooled off too quickly. It shouldn't have a lot of heat. It shouldn't be active. It should be frozen. And now we know so much more. So while Cassini is still there getting data on Enceladus, those of us who are used to thinking about Europa are going, wait, this could be happening on Europa too. You know, we just don't have the data to know. Is the surface active? Are there eruptions? What's going on in the ice shell? There's so much we don't know. So I wouldn't pose it as why Europa at the expense of Enceladus, but more, Enceladus has given us even more motivation to go back and see what is really going on at Europa.
I suppose another reason to push for Europa as the next step is that there is this mission, which has come up on this program before, the Europa Clipper. What will it do for us if it can get the support that it desperately needs?
It's going to do a lot for us. It's going to do some very basic things to begin with, right? We're actually going to get image coverage global image coverage. That to me is huge right off the bat, being able to see all the different surfaces at very high resolution and in 3 dimensions. We're going to be able to get topography. We're going to be able to get stereo images. Another hallmark of this mission concept is ice penetrating radar, which is really exciting, especially for people interested in habitability. The idea is that the radar is transparent to the ice, but it wouldn't be transparent to water. So if you had subsurface lakes, which have been proposed as part of these chaotic terrains that we see manifested on the surface, if there really are lakes in the ice shell of Europa, the radar should be able to ping down and find those. And we would be able to start mapping out the plumbing of Europa's ice shell.
To clarify, this is based on this hypothesis that not all of the water, not all the liquid water is deep, deep down in the ocean, but some of it may be quite a bit higher, quite a bit closer to the surface in these lakes that you mentioned.
Exactly. So shallow subsurface lakes could potentially exist on Europa in the ice shell. Those might be really great places to find organisms if life exists there. That's really exciting.
Finally, it's 2015, and we've just gotten the good news about Europa Clipper. The mission is going forward. Matt Kaplan caught up with Bob Pappalardo, the mission's project scientist, at JPL's Icy Worlds Day.
Bob, I get the feeling that after a long, long wait, congratulations are in order.
Thank you. I think so. This has been a wonderful day, a wonderful few hours. We've been working on concepts for missions to explore Europa for about 15 years. And today the NASA administrator said we're going forward to the next phase, which seems to mean Phase A, as it's called, becoming an actual mission. And that, he said, instruments will be selected in the spring.
This spring of 2015.
That's what he said.
Have you guys overcome the big challenges? And they are big challenges making a mission like this work.
Oh, absolutely. One of the biggest challenges is the radiation environment at Europa. And the concept we had been talking about was a Europa orbiter. If you're orbiting Europa, then you stay in the radiation environment for the whole mission. So the whole mission can only be a few months long, or guaranteed to be. Instead, now we're talking about a multiple flyby mission that dips into the radiation zones. As it's orbiting Jupiter, it flies by Europa, dips into the radiation zones, and then out again. And does that, in our candidate mission scenario, about 45 times. And that way you build up coverage through those 3 years of Europa encounters. The mission designers have been so clever and so responsive to the desires of the science community. The science community says, oh, that's great, you can make flybys of Europa, but we want to see all parts of Europa. And we want the orbits to be like this and crossing like that. And through that iteration, we have come up with a really outstanding mission design for covering most of Europa's surface. Multiple flybys, kind of like Cassini has been doing at Titan, right? The Cassini spacecraft at Saturn flies by Titan lots of times, and we're putting together this global map of that moon. But this mission would carry instruments to address scientific questions specifically related to Europa's ocean and its potential habitability.
This thing we're standing next to, this mock-up, would seem to be additional evidence of how far along this mission is. Tell us about this.
Oh, absolutely. So this is a mock-up of what we call the vault. The concept comes from the Juno mission, which is headed to Jupiter and has a vault to protect its electronics. That is, there's a lot of shielding there. And so we're building on that in the Europa mission concept. So the vault would have a bunch of shielding, a bunch of metal that protects the sensitive electronics of the spacecraft, the brains of the spacecraft. This is kind of the skull of the spacecraft, if you like. The most sensitive electronics would be buried the deepest with the most shielding. But of course, the instrument sensors would be out in the breeze, as we like to call it. And so the instrument proposers need to worry about that. And those instruments will then get incorporated into the one vault as we're envisioning it now.
We'll be right back with our Europa Look Back after this short break.
Hi, y'all. LeVar Burton here. Through my roles on Star Trek and Reading Rainbow, I have seen generations of curious minds inspired by the strange new worlds explored in books and on television. I know how important it is to encourage that curiosity in a young explorer's life. That's why I'm excited to share with you a new program from my friends at the Planetary Society. It's called the Planetary Academy, and anyone can join. Designed for ages 5 through 9 by Bill Nye and the curriculum experts at the Planetary Society, the Planetary Academy is a special membership subscription for kids and families who love space. Members get quarterly mailed packages that take them on learning adventures through the many worlds of our solar system and beyond. Each package includes images and factoids, hands-on activities, experiments and games, and special surprises. A lifelong passion for space, science, and discovery starts when we're young. Give the gift of the cosmos to the explorer in your life.
With the good news about Europa Clipper lighting up the imaginations of planetary scientists all over the world, the scientific community began thinking about the next steps in the journey. How could we take it one step further to actually determine whether or not Europa was habitable? In 2020, Jet Propulsion Lab astrobiologist Kevin Hand, the author of Alien Oceans, The Search for Life in the Depths of Space, spoke with Matt about what it was going to take to actually truly determine Europa's habitability.
Let's jump back to Jupiter and Europa. I mean, we could spend the rest of our time just talking about the upcoming Europa Clipper mission that so many of us are looking forward to. But it is an orbiter, a Jupiter orbiter, and a lot of people don't realize. What would a Europa lander be able to tell us that the Clipper probably won't be able to?
Clipper is a fantastic mission that has an incredible payload of instruments that will map out at a global and regional scale just about everywhere on Europa. It'll take images, it'll take spectra and visible to infrared spectra, and it'll also collect mass spectra as it flies by and hopefully finds plumes. And it's got ice-penetrating radar on board. So there are many different ways in which the Clipper mission will help us better understand Europa as a world in and of itself. But when it comes to actually searching for signs of life, looking for biosignatures, that's when you really need to get down to the surface and scoop up a sample and look in detail at some material that you've collected. And so a lander on the surface of Europa, or any ocean world for that matter, is really the key to searching for signs of life. And coupled with that, such a mission also provides critical ground truth to all of those remote sensing observations that have been made. And that's really critical. Think about the Mars program. We've had lots of orbiters that have done remote sensing around Mars, but it's really only once you get down to the surface and really put a rover or some sort of vehicle that can sniff around and directly analyze the geology and geochemistry that the full remote sensing data set all of a sudden makes a lot of sense. So biosignatures and ground truth are the big ticket items for a lander on the surface of Europa.
It was looking pretty good, at least in Congress, for a Europa lander mission to get some kind of a start a while back, and maybe doesn't look quite as good now. But from what you told me when we were talking just before we started recording this conversation, there's still an awful lot of interest in the science community in a lander.
That's right. We were planning on having a conference about Europa lander, or more broadly, we like to also refer to it as an ocean worlds lander. The technology that we developed for landing on Europa can also be used for Enceladus and Ganymede or Pluto. The first mission to land on an ocean world, an airless ocean world, will be the template for many of the ocean worlds. This conference, unfortunately, due to a global pandemic, had to be canceled, but we were just thrilled to see how much excitement there was in the number of people that registered for the initial conference and the number of people that are signing up to listen to the latest in the development of the Europa lander mission concept. So it really is a roller coaster when you look at the ups and downs of these mission cycles. And oftentimes the scientific community doesn't want to do one thing, they want to do a different thing. But one of the things that we're finding is that when it comes to the search for life within these alien oceans, the microbiologists, the oceanographers, a whole new sector of the scientific community is getting engaged with planetary science and astrobiology. And that's a really powerful kind of scientific transition. Normally, when we think about planetary science, we think about a field full of remote sensors, of people that are used to flying by worlds and analyzing pictures captured from afar and spectra captured from afar. Obviously, Mars has made a bit of a transition, and Mars has become a real world for geologists. Earth geologists love to work on Mars now because we've got in situ robotic capabilities. Well, when it comes to landing on Europa or Enceladus or any of these worlds, we're seeing a lot of excitement from the Earth oceanographic community and microbiologists and cryospheric scientists, et cetera, because it represents this possibility of getting down to the surface and really understanding the physics, the chemistry, the biology, and so on and so forth.
Let's say that Europa lander that you're advocating for lands, and sure enough, find some pretty complex molecules, organics on the surface of that moon, that lead us to believe that something is swimming around in that ocean down below. Now moving into your speculations, do you believe that those oceans, if we had something that melted its way through the ice and went down there, that would you be surprised to find that it was more than microbes, that maybe we'd find multicellular life?
Well, as you know, I love this question, and
I suspected.
to be clear, I would be through the moon, to use an appropriate phrase, with finding even the tiniest of microbe on or within a distant alien ocean, because such a discovery would revolutionize our understanding of biology. But specifically with the case of Europa, there's a really interesting dynamic going on, and that is that the surface ice of Europa is being bombarded by charged particle or radiation from Jupiter's magnetosphere. And make no mistake, the engineers don't like that radiation because it poses problems for robotic vehicles. But when it comes to the chemistry of Europa, and perhaps the chemistry of Europa's ocean, what we see spectroscopically on Europa's surface is condensed phase oxygen, O2, hydrogen peroxide, sulfate, a bunch of compounds that are made as these charged particles split apart water, and some of the O recombines into O2, and OH combines with OH to make H2O2 peroxide, etc. And if some of those oxidants, if some of that oxygen makes it into the ocean below, now you might actually be charging up that ocean with enough chemical energy to potentially give rise to multicellular life. All we have to do is look at the evolution of life on Earth and see that it was really the rise of oxygen in our own atmosphere, made possible by photosynthesis, by cyanobacteria pumping oxygen into our atmosphere. That abundance of oxygen helped drive the evolution towards multicellular life, and that's what drove the Cambrian explosion, which of course then led to us and all these large creatures. Well, on Europa, photosynthesis is not likely a viable niche, given that its ocean is beneath a relatively thick ice shell of at least a few kilometers or so. But this radiation-produced oxygen might allow for multicellular life to exist there. And it's a lot of fun speculation, but there's enough tethers there to real data that I think it's worth pondering.
The year is 2021. The Europa Clipper team is navigating the complexities of producing a mission while the world grapples with the COVID-19 pandemic and dealing with the harsh environment that the spacecraft will encounter when it gets to Jupiter. Mission System Manager Al Kangahwala spoke about the strides that the mission had made and the challenges that they were still working to overcome.
Europa has been a destination of high interest for decades, and many different mission architectures have been proposed for studying Europa, including that of a dedicated orbiter. one of the challenges is dealing with the fact that Europa is orbiting in this high radiation environment due to the strong magnetic field of Jupiter and the high energy particles trapped in it. If you're orbiting Europa, you're in the midst of that high radiation environment. And so your time is limited unless you brought more and more shielding. And if we were going to expend mass on the spacecraft design, we would rather put that mass into instruments, scientific instrument, and that would be preferable to more shielding. Teams that have studied these types of missions in the past have struggled with it. And one idea that came out was to just dip in, do your science during a period of, like, let's say, a day or so around closest approach to Europa, then leave the high radiation environment and downlink data at a more, let's say, more relaxed cadence, and then repeat. After a few dozen flybys, you could start to accrue the coverage that you would have achieved through a dedicated orbiter anyway. So we feel like we're getting the best of both worlds. No pun intended.
So let's say that Clipper, on one of its passes, finds some particularly interesting feature on the surface of this moon. A plume, let's say. We should be so lucky. You got to know that Bob Pappalardo and the rest of the science team are going to be pounding on your door and saying, how soon can we get back to that? So how soon would you be able to get back to a feature like that?
That's a great question. And that's really at the heart of the mission operations design, is working with science to understand what can we respond to quickly, what really deserves more time to respond to. If a particular instrument encounters something interesting, like they detect a new species on a particular flyby and want to reoptimize their sensors, the operation of their sensors to be more receptive to particular species, we can do that. We can support that with relatively little effort. I mean, our baseline design really accommodates that. Some of our instruments have gimbals, like our narrow angle camera. What we can do is also support updating the mosaic of images that are going to be generated from flyby to flyby. We have some ability to readjust that mosaic to respond to findings from images that have been downlinked along the way. It won't be instantaneous, but we do intend to allow for reoptimizing those profiles. Moving the trajectory is probably one of the items that requires the longest lead time, and we've worked with science to socialize that and show, making a change here means losing something that you might have already pre-planned and accounted for. So we certainly have studied astrodynamics mechanisms to help us cover new things, but I think studying it and having a well-instrumented, in the case of a plume, having a well-instrumented dedicated plume flyby is something that require more lead time to plan and work out with science. So to me, responding to findings is part of our job. There's a spectrum of response time constants, and the plume scenario is probably one of the ones with the longest time constants.
It was 2023, and the European Space Agency was celebrating the launch of its Jupiter Icy Moons Explorer, or JUICE mission. The mission isn't solely dedicated to Europa, but the data that it's going to collect about Europa, Ganymede, and Callisto could someday help us better understand the differences and similarities between the Galilean moons, many of which we think have subsurface oceans. We're still awaiting that spacecraft's arrival at Jupiter, but it did complete a beautiful flyby of Earth and our moon just recently, slingshotting it ever closer to its target. JUICE project scientist Olivier Vitas shared the details about the launch and what it was going to teach us about Europa.
We are pretty sure there is liquid water at Europa, relatively sure that there is liquid water on Ganymede. Callisto, there is a question mark, so Callisto is also quite interesting. And the first thing to discuss when you want to discuss habitability is to really understand the properties of liquid water. So because we don't know where it is, so at which depth, or we have some ideas, of course, some indication. But for example, the subsurface ocean at Ganymede could be at 100 kilometers underneath the surface, but it can be 110, 20, 120, 150. So we need to know. It's important. We don't know exactly the depth of those oceans. So is it 100 kilometers, 50, 80? We need to know, because we want to know the amount of water that you have there. And also the composition. We know they are salty because we detect them with the magnetometer. So we know they are salty. That's an interesting piece of physics and detection, by the way. But we don't know how much salt do they have there. And the composition is quite important to characterize liquid water. Is it an interesting water for life, etc.? We'll also be studying the radiation environment because it's good to know the radiation environment. I mean, on Earth, we are happy to have the magnetic field. Then we have less radiation coming from the sun. So what is the case at Europa with when there is no internal magnetic field and Europa is close to Jupiter? What is the case at Ganymede, which is a bit further away, much further away, with an internal magnetic field? That's the only moon to generate its own magnetic field, so very, very special. So what is the role of this magnetic field? Does that help to protect? Not at all. How this interaction between the magnetic field of Ganymede and the magnetic field of Jupiter? And what is the case at Callisto, the moon which is the much further away with the Galilean moons? So in principle, it's better for the radiation environment at Callisto, but at the same time, the moon is far from Jupiter, so the tidal activity is very weak. The moon has probably not evolved since its formation. When you look at the surface of Callisto, it's plenty of craters. So that means the surface is very young. Probably there is not much geological activity. So is there a liquid water underneath the surface or not? That's an interesting question. And the finding either yes or no will be interesting. And then you can compare the three moons. So Europa, which is active with the possible geysers, very interesting ocean, but close to Jupiter. Then you have on the other end, you have Callisto, which is dead. We don't know if there is an ocean. In principle, it's not very interesting for habitability and life, but who knows? And then you have Ganymede in between. So a big question mark. So that will be a very interesting to know more about the three moons and then to compare them and to understand better the question of habitability and whether around Jupiter there is interesting place to study life. And then to study life, we will need another mission.
The data from upcoming missions like JUICE and Europa Clipper are going to be very helpful, but there's still a lot that we can learn from previous flybys. Kevin Trin, who was a PhD candidate at Arizona State University, was still piecing together the information from the Galileo spacecraft in 2023. He told us a bit about Europa's formation and how it evolved over time.
Our idea of Europa evolving slowly is pointing out that a small moon like Europa could have formed as a cold mixture of ice, rock, and metal, or a cold mud ball, put it that way. And over time, as we have heating from radioactive isotopes and tidal heating, we'll eventually melt stuff and slowly convert into a layered structure. The alternative is to assume that Europa was layered to begin with. And that's a pretty common assumption in the literature, but it's a hard one to support given that if we assume all of Europa's accretional energy got converted into heat, then we still might not have enough of a temperature increase to have that layered start. So I find it hard to argue for what's typically assumed, which is Europa started out layered. Instead, we have to overcome these hurdles. So while there's a lot that we don't know about Europa, we do have a good idea of how much, what the mass and radius of Europa is, and that's going to put some constraints on Europa's formation conditions.
What is the formation timeline that you think is most likely given the data that you've analyzed?
Europa most likely formed, I'd say, between 3 to 5 million years after calcium aluminum inclusions, or CAIs. Those are the first solids to have condensed in the solar system. So they provide, I guess, a time reference point for us. But it's also a physically significant one because the earlier we form in the solar system, the more aluminum-26 we have. That's a short-lived radioactive isotope. And that contributes a lot of heating, and it's very sensitive to our uncertainty in the formation time of Europa.
This paper proposes that Europa's oceans may have this metamorphic origin. And I'm sure a lot of listeners are throwing back to their early science classes about rocks. But what would it mean if Europa's ocean had this metamorphic origin?
To put things in context, when I use the word metamorphic, I mean that the ocean itself formed as a result from warming up the rocks. The alternative is that we melt ice directly, and since water is much less dense than rock and metal, the water should migrate to the surface, and that can form the ocean. Now, if you form the ocean metamorphically, we're taking the oxygen, hydrogen that's directly bonded to the hydrogen minerals inside of Europa's rocky interior. And at high temperatures, the hydrogen and oxygen will be released from the rock, and that can be combined into a fluid, probably a supercritical fluid, depending on the pressures where the rock is dehydrating. But this fluid is really hot. It's really reactive, and it's low viscosity, less than water. It's going to want to shoot up to the surface. I haven't done modeling myself, at least not in-depth modeling, on the dynamics and timescales of how that fluid migrates from the interior to the surface. But the ocean formation process for a metamorphic origin is going to have high temperature and pressure conditions. So that's going to govern the rate at which chemical reactions proceed. And that's going to be a very different physical scenario compared to forming the ocean by melting ice and having that water percolate to the surface.
Finally, it's 2024. We're almost back at the present. Europa Clipper is just a few months away. Scheduled to launch in October 2024 and arrive at Jupiter in 2030, the mission team is putting on the last finishing touches on the spacecraft. Project scientist Bob Pappalardo's joy was absolutely palpable the day that he came to our headquarters in Pasadena, California. He brought a replica of the Europa Clipper vault plate with him, humanity's next message sent with all of our love to a world beyond our own.
When we were inquiring along with our communications team, might we be able to have a message on our spacecraft, the spacecraft team came back and said, yeah, one of these vault plates, you can have both sides. And it's about like an 8.5 by 11 piece of paper cut diagonally with kind of rounded corners. So that's pretty much the area we had to work with. And we worked with our communications team to throw out ideas for what kind of messages we might want to include there.
In a lot of other cases, we've sent these messages out into space. Voyager is a great example. This vault plate is being compared to the golden record that we sent out into interstellar space at this point on the Voyager spacecrafts. You know, I imagine that this is more of it's kind of a message for us more than it is a message to the Europans or whatever extraterrestrials might find it, which kind of gives you a little more freedom to add whatever you want to it without having to consider how would an alien interpret this.
That's right. Our goal is not to talk to the Europans. It is to talk with ourselves. And of course, the same could be argued for Pioneer or Voyager, but yes, there's a chance that it could be found someday. But really, those two are much more to educate ourselves. So, okay, so here we'll go with that and say, what do we want to communicate? What do we want to talk with the public, talk with our inhabitants of our planet about in thinking about space exploration? So we knew past spacecraft have collected signatures and said, send your name to space. And we thought, well, we're not any mission. We want to do something a little more special. Instead of just sending your name, what if people are co-signing a message? They're essentially acknowledging this message that's going out to Europa and being part of that. So then, of course, the question is, what message? Who writes it? And for, I don't know, weeks to months, we were tossing out names and thinking about who might be the right person to write such a message. And then we all converged on the poet laureate of the United States. Let's see if she would agree to do it. And our comms team reached out and gave a presentation. And I've heard interviews with Ada Lovone, who said, well, why are they telling me all this? And then the ask came, would you write a poem for the spacecraft that's going to Europa? And thank goodness, fortunately, she said yes. And then she's explained that, she said yes. Now what? How to write that message.
No pressure.
No pressure. I wouldn't want to have to do that. It means a lot to me personally that we had the poet laureate write this beautiful poem for Europa. My mom was first a proofreader and then a special education teacher, and through her whole life wrote poetry. So it's extra special to me that we have a poem going to Europa.
I hope you're all as excited about the Europa Clipper mission as I am. It's taken so many decades of hard work and dedication. Here are the words of Ada Limon, the U.S. Poet Laureate, in her poem, In Praise of Mystery, a poem for Europa.
In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
October is going to be a wild month for planetary science. We've got the Europa Clipper mission to look forward to, but also ESA's Hera mission that's going to view the aftermath of the DART asteroid impact, and NASA's Escapade mission to Mars, along with a few others. It's going to be a very exciting time. Also, personally exciting for me, next week I'm going to be hosting the webcast for NASA's Innovative Advanced Concept Symposium. I'll chat about it with our chief scientist, Bruce Betts, up next in What's Up. Hey, Bruce.
Hey, Sarah.
Man, it is a busy time right now. I'm preparing for NASA's Innovative Advanced Concept Symposium.
Nyack.
Now, I know Matt loved going to that conference. He did it for years, and now I get to host the webcast. And I don't know, like, it still kind of blows my mind that I get to host NASA webcasts every once in a while. Like, do you ever have that moment where you're just like, how is this my life?
Yeah, I'm having it right now.
Right.
Yeah, what are we talking? Nyack. Go crazy. Yeah, well, Matt does love his Nyack. It's rather far future focused.
That's what's really interesting about it for me. It's almost like space Shark Tank in my brain. Since it's going to be in Pasadena this year, right near our HQ, it seems like Matt's going to be able to come up and attend for a little while. So we'll both get to be there at the conference.
That's good. That'll be fun.
Yeah. I wonder what kind of projects they have for this program that just don't make it through, right? I bet there are just hundreds of these projects, and you've probably dealt with a lot of that too, because we have these grant programs. Some of the wackier projects do kind of make it through our ideation process. Like, I mean, come on, if you get Bill Nye talking about laser bees, that project's...
Hey, we funded that project.
Okay, for people who don't know, what are laser bees?
No. Laser bees is actually a very interesting concept for deflecting asteroids that are potentially headed towards Earth. So if you discover a dangerous asteroid, you can hit it with a kinetic impactor like the DART mission. You can do a gravity tractor. If you're late in the game, you can deal with trying to do a nuke. But laser bees was a concept of the professor at the University of Strathclyde in Scotland, and it was to have multiple spacecraft, each with a laser that was powerful enough to ablate, so basically boil away the surface of the asteroid. And you have as many as you need for however quickly you need to move it, fire up on one side of the asteroid and create a jet of gas that pushes you the other way. And so we funded, and you can find pictures on our website, the very cool lab work done by he and his grad student, who then got her PhD doing this, working in the lab and vaporizing rocks with lasers. And I mean, seriously, what's not to love about that? But it was the early phases of, can you do that? What's the momentum transfer? And they published it, so it's out there. Yeah, and that's not even the beginning of wacky compared to some of the proposals we've received.
Really?
Especially for our wide open STEP grant program. program. But I mean, I don't want to reference specific proposals, but they range from, well, they're the ones that are just unrealistic on budget. And I don't mean like off by a factor of 2 or 3 or 4. I'm talking off by factors of tens of thousands, hundreds of thousands. We're talking, well, we need to do this and we'll build 1,000 spacecraft and yes, we would like $50,000 for our grant.
For a project that's probably going to be several billions.
Billions. Some of these would be hundreds of billions projects. And some of them phrased it as they were beginning, but some people phrase it that, no, that's what we can do that. And you can't. Anyway, but we have lots of great projects that come in as well. And a lot of great ideas of which we can't fund all the ones that come into our grant program. So I don't want to portray it incorrectly, but there are the ones that are, they're wild. They're creative.
One of these days I'll come at you with a weird pitch.
Oh, you already have, Sarah. I mean, just last week or the week before, what were you doing? You were cooking in space with your cat.
Yep.
Yeah.
But that grooved with people. I saw it in the member community. People being like, but what about the cats? We need to be making sure that we can feed the cats in space. So clearly it's not just me. So about that episode about feeding people in space, we actually did get a poem related to something that I asked you, which was what was the first food that we grew on the ISS, I believe. And one of our members, Jean Lewin, wrote in a poem called Red Romaine Lettuce, which was the food that they grew in space. So here's that poem. In Salinas, California, there are acres of this crop, available in the produce aisle, but in space you cannot shop. We need to find a simple way providing food our space crews need. So growing plants was the first step. At this, we did succeed. Romaine lettuce seems prophetic for that gastronomic scene, because as we find each fiscal year, NASA could always use more green.
Nah.
So true.
Nice. That's why they were growing it.
Right? Oh, man. How much would you give for a head of romaine lettuce on Mars? Like,
whoa.
Yeah.
I was like, nothing. But then you put it on Mars. Like,
right.
Actually, it's even less than nothing because I'm here.
It's true. Well, anyway, what is our random space fact this week?
Random. Space. We're going to talk about a scale model. Everybody loves scale models. Give you an idea how freaky large and distant things are. What if the sun were the size of a basketball, and that basketball is sitting at one end of a basketball court? What would be going on with the Earth? Well, it turns out the Earth would be roughly the size of a sesame seed to a popcorn kernel kind of size, and it is roughly at the other end of the basketball court. So basketball at one end, Earth at the other end, and Earth being a tiny seed-like object, and that is a scale model in basketball land. Shoots from the outside and scores!
Swish. Really, though, usually scale models make me feel like, wow, that's so much bigger than I thought. But this is one of those examples where actually, like, that's smaller than I thought, the distance between those two things.
If it makes you feel better, Neptune would be 30 basketball courts away.
That's a great way to think about it. And also somehow makes it seem shorter, even though it is ridiculous. Bigger than a sesame seed for sure, though.
Yes, it would. Yeah, I don't offhand know it's roughly 4 times the diameter of a sesame seed. And sesame seed, not the best analogy because it's not round, a nice sphere.
Maybe a caper.
Caper. Neptune is a caper 30 basketball courts away. Full court.
Can you tell I'm hungry? We've been talking about romaine lettuce. I'm going to make some kind of salad tonight. Anyway.
Apparently with capers and maybe some sesame seeds.
Sounds great.
What dressing do you put on that? Interstellar medium?
Interstellar medium. We need to create a side hustle. Planetary Society, hot sauces and salad dressings.
Whoa.
Yeah.
Okay, I'm going to think about that. Like, you should go out there, look up the night sky, and think about planetary salad dressing. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with even more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who've been advocating for Europa Clipper for years. You can join us and help many more amazing missions launch to success at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.